Hey folks, welcome back. Today we are going to discuss one of my favorite topics in archaeology, radiocarbon dating. Well, radiocarbon dating was invented in 1949 by notable chemist Willard Libby, who later won the Nobel Prize in Chemistry for his achievements. The method that I'm going to describe to you, the radiometric method, has been used not only with radiocarbon, but it's the principle of virtually all other radiometric dating methods. It completely revolutionized dating science and moved archaeology so far forward, so to speak, that in some ways there's some negatives that came out of it, even though now we could get absolute dates with a relatively high level of accuracy. Some of the old techniques that archaeologists used to use, like taxonomy and seriation, those things have largely fallen by the wayside during my lifetime. And nowadays, people depend very heavily on radiocarbon dating and other techniques. It's based on the principle that some elements are radioactive It's based on the principle that some elements are radioactive. And even though they can exist in one form today, they can decay or transform into another element over time. The time that it takes for this to transform is measured in what they call half-lives, or a half-life. Each radioactive element has a half-life, which is the approximate amount of time that it takes for half the mass of a radioactive element to decay into a stable form. Decay, half-life. Terms used in nuclear physics. So, the amount of time that it takes for half the mass of a radioactive element to decay into a stable form. Now, stable carbon is carbon-12. And one radioactive isotope of stable carbon is carbon-14. Carbon-14 is radioactive carbon. Now, there's more than one, or there can be more than one isotope for a radioactive element. But in this case, we're talking about carbon-14. Carbon-14 decays to nitrogen-14, which will make sense in a minute perhaps. But the half-life of carbon-14 is 5,730 years. So if you had I don't know, 500 atoms or 500 grams, whatever, of radioactive carbon 5,730 years ago, and today you would expect to have about half of that. Did I say 500? If we had 500, we had been 5,730 years, we'd expect to have half that amount, or 250. In another 5,730 years, which would be 11,460 years, we'd expect to have a quarter of the amount, and so on. It's a little bit like, suppose you had a pail of water with a leak in it. And that water dripped out through a leak in the bottom, say 1 drip every second. You could then calculate, if you knew that there was, say, 2 gallons of water and 1 drip equals 1 mil. Let's make this liters instead of gallons. If you had 2 liters of water and it dripped out at 1 drip per second and 1 drip contained 1 mil, you could then do a quick calculation. It would take 2,000 seconds for this to be empty. Or about 33 1/3 minutes. So, in other words, if you know what you have to begin with, and you know what you have, and you know the rate of decay, and you know what you end up with. Well, actually, if you know these two, you can calculate what you're going to end up with. But let's suppose you don't know what you, as long as you knew what you begin with, and you knew what you ended up with, you could actually calculate the rate of decay. All right, am I not making sense? With a little bit of algebra, you can calculate the amount of time it takes for this to drip out, or if you know how much is dripped out, you can calculate how much was in it to begin with, or if you knew how much that was in it, you could calculate the rate of decay, and so forth and so on. Gosh, I'm not sure if that was a very good example. So let's move on to the next one. How does all this radioactive carbon get into something? Excellent question. I'm glad you asked. It all begins with the sun. Well, maybe not the sun exactly, but let's just say the sun and the atmosphere. The atmosphere on Earth is considerably made up of oxygen, nitrogen, carbon, carbon dioxide, and a few other things. For the most part, we're looking at nitrogen to the tune of something like 78% of the entire atmosphere is made up of nitrogen. Of course, it also has a certain amount of carbon in it. But let's focus on the nitrogen for a minute. The atomic number for nitrogen is 14, which means, the atomic number is 7. It's the atomic weight is nitrogen 14, because that's composed of 7 protons and 7 neutrons. And also, coincidentally, 7 electrons, but for now, let's just deal with the protons and the neutrons. These add up to make its atomic weight of 14. Now, according to physicists, physical chemists, I should say, these cosmic radiation or solar radiation are constantly bombarding our atmosphere. And when it contacts nitrogen, in some cases, in about 1 in every trillion nitrogen atoms, a proton essentially gets knocked out, leaving us with 6 protons and 7 neutrons. Or perhaps I should say this energy comes in and converts the proton into a neutron, or it adds a neutron to the neutrons. In either case, you end up with 6 protons and 8 neutrons. Now, this chemistry is really not the key importance to us. What's of key importance to us is that this here, which determines its atomic number, if nitrogen is 7, carbon is 6. So what's really happening is that 1 in every trillion nitrogen atoms is being turned into an atom that behaves like carbon. It still has an atomic weight of 14, but it has 6 protons, which makes it act like carbon. So we call this carbon 14. Now, carbon 14 is a radioactive isotope. It doesn't want to remain carbon 14. It wants to return back to being nitrogen, which it will do. This carbon 14 is an isotope of carbon, and a radioactive isotope at that. Eventually it will release a beta particle, and it will return to being nitrogen 14. The amount it takes for that to occur is referred to its half-life, which is 5,730 years. About every 5,730 years, about half of these carbon-14 atoms that were created will convert back into nitrogen-14. This is an ongoing process. At any given time, about 1 in every trillion atoms of carbon in the atmosphere are in fact not carbon. They're radioactive carbon, which are actually nitrogen, but they're treated as carbon, and they are in the process of decaying back into nitrogen. Why is this helpful for dating? Well, I'm glad you asked. All right, so you've got the solar radiation coming in, impacting nitrogen-14, converting it into carbon-14 to the tune of 1 per trillion, 1 times 10 to the negative, 1 to 1 times 10 to the 12th? I believe so. All right. So 1 in 1 trillion atoms are radioactive. Now, meanwhile, on Earth, you've got trees and living organisms that are incorporating carbon into their daily lives. Let's see, Charles. So what kind of an animal is this? This is just for fun, this is an aurochs. That's in It's a cattle-like, it's an extinct cattle-like creature that's a precursor to modern bovines. Whoops, I'm out of time. All right, so I will pick this up next time we meet. Until then, have a great day.